Good morning, people. I'm sorry we are slightly late. There was a small hitch, and fortunately, our people have got the system back working. Okay, we stopped somewhere last Tuesday onto this chapter or session on consolidation. Apologize, compaction, and we looked at the we started by looking at a few aspects. Let me just recap and spend 1 or 2 minutes on what we have done last week. We started off with compaction. We looked at the difference between compaction and consolidation. We went on to look at some of the behavior of the compacted soil, in particular how the soil fabric changes as the as the water content increases with the degree of compaction, or as the as you before as you are prior to the OMC or the maximum dry unit weight, and as you cross the transient load or the transient maximum dry unit weight, how the fabric then becomes more oriented. We left somewhere when we started with the engineering behavior of the soil, and today I intend to spend the next 10 minutes just to complete this section on engineering behavior of compacted soil. Let me just, this is the same file which was uploaded last week, but again, in case you were not able to download, it's I've right clicked and you should be able to download right now. Okay, we looked at on this slide, when we looked at the bottom figure shows the dry density or the dry unit weight. I would not like you to look at the numbers. Numbers hardly matter, and the horizontal axis is the water content, and that's a nice compaction curve. Okay, probably for a silty kind of deposit with some amount of clay. So as we see, with the increase in water content, you had a peak. The corresponding figure on the top shows the permeability. So again, you're not looking at the numbers, but what the difference shows is this horizontal line and the other horizontal line. The difference shows is the one order of magnitude. So what we see is, as the water content increases from left to right, is the same axis drawn above. The I have a question over here, it's gone. Okay, as the water content increases from left to right, what we see is the permeability drops by more than 2 order of magnitude. The minimum permeability is somewhere beyond the OMC. So OMC is somewhere there, somewhere beyond the OMC is the minimum permeability. So we are not going to, we probably will not concentrate too much on why this permeability is slightly, the minimum permeability is slightly beyond the OMC. But what the idea is, you are looking at a value. If you need to compact the soil at which has a least amount of permeability, you would normally compact it at a term or at a value slightly above the optimum moisture content, say about 2% or so. Okay. Thereafter, the permeability slightly starts to increase, but the minimum value is somewhere 2% above the OMC. This is just to put it in English. As the compactive effort increases, meaning you go from light compaction to heavy compaction, your permeability obviously will decrease because of the improved orientation of the particles, and more particles are packed. The second property or engineering property we look at is the compressibility. So the vertical axis over here is the void ratio. I would like you to look at the top figure, and the bottom axis is the pressure. Okay. Now please note, the pressure is in normal scale. Why I stress on this normal scale? Because we look at another figure, the bottom figure, where the pressure is not in normal scale. So this is a normal scale which you can get it from the normal, you can draw XY plot. What we see is the sample which has been compacted dry meaning the prior to the OMC, if it is compressed. So you have the starting value of void ratio being the same for this curve and the other curve. The other curve is for sample which has been compacted beyond OMC. So it's wet side of optimum, and the other one we call this as dry side of optimum. So what we see is the sample which is on dry side of optimum shows less of compressibility, less change in void ratio with compared to the sample which has been compacted wet of optimum. What you see is there is a large change in void ratio in this figure compared to the other figure. Obviously it means that the dry compacted will compress less compared to wet compacted, but there is a rider, important rider. The rider is the load is less. So just let me just club these 2 or 3 statements. If the load is less, the dry compacted soil will compress less. Obviously because there is large attractive force, the less load which you apply will not be able to bring the particles together. So the other figure, the attractive force is less, so that is why even with a small magnitude of load, the particles you can bring them together. Let's compare this to the bottom figure. The bottom figure, vertical axis is the same void ratio, horizontal axis the pressure the same as the top one, but over here you see a log scale, and log scale meaning this whole axis is much greater than the axis which is on the top figure. So in other words, you started from somewhere here 0 and came down to this value of pressure, applied pressure. This whole range probably is not beyond somewhere here, it's just this much. Okay, I'm just making a scale representation, but obviously we are not looking at numbers right now. So the dry compacted showed less compressibility in this figure, that can be shown somewhere here. The wet compacted showed larger compressibility, probably it's somewhere here, so this much. But what you see is when the pressure increases to a large value, meaning I move from here to there. Remember this is a log scale, so in other words this becomes 10 times, 100 times, so you're increasing by large value. What we see is the dry compacted shows a greater void ratio change compared to the wet compacted. Or let me rephrase this, the dry compacted shows a greater compressibility compared to the wet compacted. In other words, the particles which were very strongly bonded because of the large attractive force in dry compacted, now those large attractive force are able to break down because of the large pressure which you apply. So under large pressure, the particles which were very attracted and you could not bring them closer, they now come to achieve a much denser configuration, or they come much closer because of the large applied load. This is an important, I would say, observation when you do maybe when you check for compressibility of soils. Okay, so obviously these are just to put it in English. You can go back home and go through this English whatever has been written. There are a few other few other simple properties of this compacted soil which we are going to briefly look at. The first one is swelling and shrinkage. Obviously the sample which is dry, meaning of optimum, has thirst for water, it needs water. So when it gets water, it will swell more, that's obvious. Shrinkage would be again the clays which are dry of optimum will have a greater deficiency of water and tendency to thus absorb more water and swell. That's a swelling one. Sorry, shrinkage is here, apologize, this is the shrinkage. So soils which are wet or compacted, because they already have too much of water, they will show more tendency to shrink, there will be larger shrinkage. The strength, this is again an important thing if you are looking at the strength, if you are designing an compacted soil, say an embankment based on strength, then soils which are compacted dry of optimum, meaning slightly less than optimum, you will have higher strength. Over here the next figure, in fact it's a table, it summarizes all the properties. So the first column is the kind of property you are looking at. and the second and third column would be whether the soil is dry of optimum or wet of optimum. I would like you to look at this first, second and third column very carefully. Can you just guess, is there something wrong in this table? I'm not sure if you've gone through, but if you look at this carefully, let's look at the first property, the structure. Okay, uh, where is the pen? Yeah, anyway. Okay, this is a pen, and I have, okay, pen has single color, only black color. Okay, I hope highlighter works. Okay, please look at the first one. Okay, the first one, and I'm not going to, make you worry too much on the error right now. Please look at the first one. It says structure after compaction, and it speaks about flocculated and dispersed. Obviously, flocculated and dispersed refer to fabric. So this word is incorrect. Okay, I hope I can. It should not be structure, but it should be fabric. Okay, that was the trick in this slide. Okay, the next one is water deficiency. Okay, this is not water deficiency. We have just spoken about this. Let me skip this. What about permeability? We said dry of optimum. We said is more. Okay, let's ignore the second term for the time being. And wet of optimum we have just said is less. Obviously from the figure where the permeability dropped by 2 order of magnitude. But let's look at the second term, which is isotropic. Isotropic and anisotropic. These are important terms, and in the next slide I'll just explain the difference between isotropic and anisotropic. You just go to next slide and I'll come back to this slide again. Oops, sorry, already had this fabric. So we have it something called the left hand side is a flocculated, mean random lines. The right hand side is dispersed, meaning sleepy lines. So random lines, if I allow water to permeate in the horizontal direction, that's the blue arrow. There's another blue arrow wherein the water is allowed to permeate in the vertical direction. What we see is in both the case the path is tortuous, meaning the water will have to go there, it'll have to do a lot of difficulty to reach the other end. The same thing, water has to travel from the top to bottom. It has to undergo a much difficulty as it goes from top to bottom. Although both the randomness of this fabric makes the water flow difficult in both the directions. So it's more or less, I would say the difficulty in flow is similar for both the directions. So the flow or the permeability, if I allow water to flow from one end to the other, permeability, as we will see later, is the nature of soil, how it allows the water to flow. We'll look at it later. For the time being, just visualize that the water has to flow. And what we say is the flow of water is tortuous for both the direction. In other words, the flow would be similar, or can I just put a common word, the soil behavior is isotropic. Iso is same, tropic, so it has same behavior or similar behavior in both the directions. Let's look at the figure on the right, which is a dispersed fabric. So more or less you have sleepy lines. So the water which has to flow horizontally, now it's much easier. It just flows and smoothly flows out. Whereas the vertical one, it has still tortuous, it has to travel, okay, left, right, left, right. Remember, these two cartoons are just to drawn to some scale, just to represent the water flow. It does not necessarily mean the water will flow exactly in this manner. Okay. So what we see is the horizontal flow is smoother, or can I say the permeability or the flow would be much faster in the horizontal direction than in the vertical direction. So in this case, the behavior, the permeability is not isotropic, so we call this as anisotropic. Okay. Usually difference in the two order of magnitude is approximately, sorry, the difference is about approximately 1 order of magnitude. Okay, so over here we have the fabric. So if you go down, you have other look at, we have done compressibility, so low stress or low value, you have low compressibility for dry. Likewise, it becomes opposite for wet, for sorry, for higher compressibility. Shrinkage and swell, we have done this. Stress strain behavior is more steeper if you have a soil which is compacted dry of optimum compared to wet of optimum. Dry of optimum, it also gives a more brittle behavior compared to wet of optimum. That's an important, observation. So when we say steeper for the leftmost this column, it would give a higher elastic modulus compared to the elastic modulus of wet of optimum. Likewise, you can go home and take a look at the remaining 2 columns as well. Okay. Now I like to pause over here and do a few problems on a problem sheet. So please let me upload the a problem sheet. Meanwhile, if you have any question, we'll spend a minute. You can take 1 or 2 questions. We have I have listed down. Yeah. I've listed down 4 questions. 1, 2, 3, 4. Okay, this should fit in, right? Yeah, no, this should fit the whole page. So it's not fitting. It's fitting. Okay, you don't do anything with the mouse. Okay, so we have these 4 questions. Let me just scroll down 1, 2, 3, 4. Okay, the first question is fairly straightforward. Now let me just right click and allow you to download. Please download this problem sheet number 2, and we'll probably do, we have about 35 minutes, remaining 35 minutes. So I hope to do at least 3 questions today, okay, out of these 4. Okay, can please go through question number 1. No, they want to see this then, right? No, they can't see this. Okay. 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 Please go through question number 1. It says you are asked to compare the compactive energy in IS heavy compaction with the IS light compaction. Compactive energy is energy, right? It's energy, so it has to deal with something like what is the impact force you place when you impact force you apply when you place the rammer over the soil. So can I just solution 1? Okay, it's fine. So compactive energy it's energy. So it's something like potential energy because you drop a rammer from a fixed height. Potential energy, elementary physics tells us, is mgh. Okay, times the number of blows you give and the number of layers because you drop this number of times. So I'm going to give this into number of blows times the number of blows per layer. Okay, times the number of layers. Because you did provide this energy over fixed volume of soil, so that's divided by volume of the soil. So if this is my basic equation which I use, can I say compactive energy for IS heavy compaction? Okay, this gives a value of the mass of the rammer is 4.9 kg. I hope you had a jotted down the number in earlier part of lecture series when we said the IS heavy compaction rammer is 4.9 kg. The G is acceleration due to gravity, that's 9.81 times the height of fall is 45 centimeters or 0.45 meters times the number of blows per layer. So you provide 25 blows in the small Proctor mold and you compact this in 5 layers. That divided by volume, volume is 1000 cc, or in terms of meter cube that will be 1000 into 10 power minus 6. Okay. If you solve for this, you have a number which should give you a value of 2703881.25 Newton meter per meter cube. Okay, or because this is Newton, I can rewrite this in kilonewton. That equals to, I just need to push the decimal place by 3. So I have 2703, that's 123.88 kilonewton meter per meter cube. Remember, this K in kilonewton is not in capitals, it's small. Okay, that's the most common mistake we all do. This K is small k, not capital K. So what about the second one, compactive energy for IS light compaction? If you follow the same analogy where mgh times the number of blows per layer times the number of layers, I have the mass of the rammer as 2.6 kilograms into 9.81 is the acceleration due to gravity times the height of fall, which is 31 centimeter or 0.31 meter, times you still provide 25 blows per layer, but in this case you have 3 layers. Okay, this whole thing, if I divide by the same volume, because you use a small Proctor mold, times 10 to the power minus 6. So you have an answer which should be, again in terms of kilonewton, should be 5. Let me first write in terms of Newton, 593,014.5, that's Newton meter per meters cube, or equals to, I shift this by 3 decimal place, 593.01 kilonewton per meter cube. Okay, so if I need to compare, I can just summarize these two in terms of a statement that IS heavy compaction test uses, so I have a number 2703.88 divided by 593.01 equals to 4.56 times more compaction effort to that used in IS light compaction test. Okay. If you're happy with it, with this, I would like you to go through question number 2. Okay, it's pretty longer one. Okay. The question is slightly long, but believe me, the answer is fairly simple. What it says is, okay, what you have is, it speaks about a borrow area. Borrow area is the source area wherein you would like to bring in earth from somewhere and then use it at your site. So it speaks about borrow area. The soil at the borrow area has water content, void ratio and specific gravity given. Now this soil has to be brought from there to your site and then recompacted to a finished volume, a final volume of 50,000 meter cube. Okay, and obviously it has to be brought in some trucks. So it says it has to be excavated and transported or brought through some trucks. So when these trucks, each truck can carry a total weight of 65 kilonewton. That's the total weight of each truck which it can carry. And it says the whole construction process requires that the water should be topped up to 18%. So from 15% there is an increase to 18%. And the final, that's important, the final dry unit weight is 17.6 kilonewton per meter cube. These are the values which have been given in the first paragraph. Okay. Now we are not going to worry too much on all this, but let's look at the first one, A. It says calculate the number of truckloads, so number of trucks to be required. Okay. For any such question, whenever you have a question which is based on something being excavated, recompacted, there are two important things to remember, and those important things will be something which will be a tagline for each and every question. Okay. As we move along, we are going to look at those two important things. But first of all, please look at what are the embankment properties. The solution to, embankment properties. So you have the first one, the dry unit weight of the embankment is given as 17.6 kilonewton per meter cube. Okay. You have also been given that the finished volume of the embankment, that's the total volume of the embankment, is 50,000 meter cube. That's the thing given. Now if you recall, dry density or the dry unit weight is the weight of solids, that is the weight of dry soil over the total volume of the soil. Okay, so in other words, total volume of compacted soil is 50,000 meter cube, dry unit weight is 17.6. If I multiply by 2, multiply these two, I get the dry weight of the soil. So the dry weight of the soil, okay, if you recall, we had a symbol called W suffix S. So WS equals to 17.6 times 50,000. Okay, if you multiply the two, you should get a number which is 880,000 kilonewton. Remember, K is not capital. Okay, Newton, N is capital. So over here, I'm going to make that statement. Remember the statement which I said, when you excavate the soil and transport to another area. Okay, so the important statement is excavate the soil and transport, meaning that the weight of the dry soil or the weight of solids should not change. So just to write it down, the weight of dry soil or solids remain the same. Obviously, right, you're not going to dump the soil somewhere, remain the same. So after compaction, before compaction, the dry weight of the soil remains the same. And in relation to this, I can also write volume of the solids also remain the same. Obviously, when you compact the soil, you're not going to crush the soil particles. So if there's no crushing of the particle, under most engineering loads, the soil particles are assumed to be not uncrushable. You can't crush them under routine loads, unless you're dealing with some kind of calcareous deposits. Example, these deposits are mainly found in marine environment. So the made of seashells, those are the ones which will crush. So if this is an important statement, and I would like you to carefully look at this and understand this statement, because it's something which will help you to solve these problems. Okay, so when we say the weight of the dry soil does not change, so 880,000 kilonewton remain the same even after compaction. So let's go back to the borrow area. Okay, so borrow earth properties. We say this is the dry soil post compaction. So borrow earth, the weight of solids will also be the same thing. If dry weight is the same thing, I am given water content of 15% of the borrow. Okay, borrow earth. If you look at the question, it says 15% is the water content. So if I multiply this, okay, into, I make this into 1 plus water content, I should get the wet weight. Okay, if you remember your basic elementary equations which you looked at, so weight of soil when excavated. Okay, so that's W. It includes weight of solids plus weight of water, that equals to weight of solids times 1 plus water content. Okay, it's obviously we have done this, it's simple. Recall W equals to weight of solids plus weight of water, that equals to weight of solids. I can take this out plus 1 plus weight of water divided by weight of solids. The second term is water content. So which comes to here. Okay. So if I plug this over here, I get W equals to weight of solids, which is 880,000 times 1 plus water content, which is given as 15%. Remember, this equation will never accept percent, it's in ratio. So that gives a value of 1012, 1000 kilonewton. So that's the total weight of the soil. Okay, and the question says each truck can carry 65 kilonewton. Okay, so number of trucks A, therefore number of truckloads equals to, again the same number, 1012, 1000 over 65. Each truck can carry 65. If you plug in the numbers, you should have an answer like 15569.2. Okay, we need to round up because it's truckloads, so that equals to 15570. Okay, let's look at part B. Part B says how much of additional water do you require? Okay, so initial water content is 15%, final water content is 18%. Okay, so water, if you remember water content, okay, equals to weight of water over weight of solids. Okay, so water content is known. I have weight of solids which is fixed for both before compaction and after compaction, meaning weight of solids from the borrow area and weight of solids in the embankment is the same. So I can determine what is my weight of water. So for the first case, weight of water at embankment, okay, equals to 0.18, that's the water content, times the same weight, that weight of solids was, yes, it's 880,000. Okay, so that gives you a number of 158,400 kilonewton. Okay, so that's the weight of water at embankment. Let's look at the weight of water of the borrow area. So I'll write the same thing, weight of water borrow area. Okay, borrow area is a source area. So this equals to 0.15, that's 15% times weight of solid is 880,000, gives you a value of 132,000, exactly 132,000 kilonewton. So a weight of water we require is 158,000 and weight of water which is available is 132,000. So difference is the weight of water which we require. So water to be added, okay, equals to 158,400 minus 132,000 equals to, okay, I have a number which says 26,400 kilonewton. Okay, please verify this. So this is the weight, but if you look at the question says the volume of water. Obviously weight of water is known, also the unit weight of water is known. So unit weight of water is gamma water is 9.81 kilonewton per meter cube. Okay, so if this is the weight, if I need to get the volume, I just divide this number by this number. So volume of water to be added equals to 26,400 divided by 9.81. You should get a number which says 2691.1 meter cube. Okay. Now these two questions I would say were fairly easy. Okay. Okay. If you go back to the question 3, I would say, or 3 and 4, both the questions 3 and 4 are similar to question 2, as long as you remember that the tagline, you know the tagline which says, where are we? It says the weight of dry soil and the volume. This is the tagline. These two, as long as you can figure this out, the next remaining 2 questions are fairly straightforward. But I like question number 4 very well. Okay, and I like to try this question 4. Okay, this question 4 is interesting. What it says is there are 2 contractors A and B. Both the contractors want to sell the soil to you, and the first contractor, the soil at the first contractor, you know, of course the soil exists at some at some density at site. So the void ratio at site is 0.85, water content, everything is given. The void ratio at site for B and water content at B is given. The cost to transport and bring the soil to you is given. Okay, the cost of water, the contractor B is very generous, he is giving us free water. Okay, we need to see which contractor is more economical. Okay, so the final volume is given, the final void ratio and water content are given. Okay, let's pause over here and solve this question. Get a good cup of water. This is solution 4. Okay, so solution 4, we have the compacted soil volume, final void ratio and final water content are given. So can I say embankment properties which are given? Okay, final volume is 10,000 meter cube, void ratio final is 0.67 and water content is 20%. If you recall, your basic equation for dry unit weight. Okay, now at that time I said we're not going to remember that, but we only remember the term for gamma bulk. Gamma bulk was identified as GS plus SE divided by 1 plus E whole times gamma W, and I said you can make a song out of it because you can GS plus SE over 1 plus C times gamma W, which gives you a value of gamma dry. This S becomes 0, so I have GS or 1 plus E into gamma W. Now I don't need to remember this, but this is the only equation which will help me to derive not only this but a number of other relationships very much related to this. Okay, so we have this dry unit weight, gamma dry equals to GS of the soil is given 2.67. So it's the same GS for both the soils, 2.67 both the soils have same GS value. If you go to the question slide, 2.67 divided by 1 plus void ratio. We are looking at the embankment, the final. So final void ratio is 0.67, okay, times 9.81. If you plug in the numbers, you will get a final dry unit weight of 15.68 kilonewton per meter cube. That's the final. We know the final volume. We know the final dry unit weight. If we follow the same analogy as last question, the final, the weight of solids, okay, weight of solids is also the dry weight of the embankment. Okay, dry weight of embankment equals to this thing times this thing. Where are we? Yeah. So I have 15.68 times 10,000. That gives you a value of 156800 kilonewton. Okay, this is the dry weight. In this question, if you look at the numbers, the cost of earth is not in terms of weight, it's given in terms of volume. So I need to speak everything in terms of volume. If this is a dry weight, equivalent volume, okay, we need to look at the equivalent volume. So for this, if you remember, we said when we derived the relationship, we said there's more than one way of doing any problem which is related to using the relationship between solid or soil, water and air. So this is one of the procedure which I'm going to follow, and this is not the unique procedure. You may use your own method. So the first one, I say void ratio equals to volume of voids divided by volume of solids. Okay, if this is the void ratio final, okay, which is 0.67 equals to volume of voids, okay, divided by volume of solids, or I can say volume of voids equals to 0.67 times volume of solids. Okay, this is, I'm going to plug in this, knowing that total volume, which is 10,000 in this case, equals to volume of voids plus volume of solids. Okay. Okay. So I know 10,000 is the final volume, is the final volume of voids, final volume of solids. I know volume of voids is 0.67 times volume of solids. So I get volume of solids plus 0.67 times volume of solids equals to 10,000. If you plug in the number, you get volume of solids equals to 5988 meter cube. Okay, or volume of voids equals to that, this value times 0.67, 4012 meter cube. Okay. Now we've done this volume of solids using the void ratio. I could have alternatively used the equation for specific gravity. Okay, so I'm going to redo this, okay, using another procedure, alternatively. Okay, remember GS equals to unit weight of solids, unit GS equals to unit weight of solids over unit weight of water. Okay, unit weight of solids equals to, the numerator equals to weight of solids over volume of solids in times the unit weight of water, denominator. This value is known to us. Okay, this is known to us, 9.81, GS is known to us. So can I say volume of solids equals to 156800, that's the weight of solids, divided by 2.67 specific gravity times 9.81. You plug in this, you should get a a similar number 5988. So I think it's just 5986.4. So that's just the because difference is because of the rounding off error, but it doesn't matter. It's just rounding off. Okay. So we have just looked at the volume of solids, and we know the weight of solids. So I'm going to rewrite this note again, okay, so that I wouldn't say you won't forget it, but at least to recap, the weight of solids remain the same, as well as the volume of solids remain the same. So before compaction, or the weight of, or from the borrow earth, the weight of solids will remain the same as well as the volume. Okay. So let's go to the borrow area. So borrow area properties. So pit A. Okay, pit A, the void ratio given is 0.85. Okay, void ratio we know equals to volume of voids over volume of solids. So can I say volume of voids equals to 0.85 times volume of solids? Okay, if you follow the similar analogy as we have used before, I have volume of solids plus volume of voids equals to the total volume. Okay. Okay, remember our objective is to find out the total volume. So I have volume of solids which is known. I'll just use this logic. Volume of solids is 59. Okay, where are you? Where are you? 5988 plus 0.85 times 5988. Okay. If you plug in your number, you should have 11077.8 meter cube. Okay, that's the total volume of soil from the borrow pit A. The cost is 900 rupees per meter cube. This is the total volume. So can I say the cost of earth? Cost of earth equals to rupees 900 times 11077.8. Okay, this gives a value of rupees 99, I think 99 lakhs 70,020 rupees. Okay, that's the cost of earth. However, this supplier also charges for the water, and remember the final water content we need is 20%. The initial water content at this site or this borrow area is 16%. So the cost of water at embankment, so sorry, cost of water is the weight of water at embankment. Okay, we'll follow the same logic or using water content equals to weight of water over weight of solids. If I need to evaluate this value, weight of water, I just multiply water content by weight of solids. Weight of solids remain the same. So embankment, I need 20% water content, that's 0.2 times 156800. It gives a value of 31360 kilonewton. Likewise, if I do it at borrow area, I have the weight of water, that's 0.16 times 156800. It gives me a value of 25088 kilonewton. Okay. So the water required will be the difference between the two, and if I divide this by divide the difference by 9.81, it should give me the volume. So final volume of water, okay, equals to the difference, which is 31360 minus 25088 divided by 9.81. Okay. If you plug in the number, you should get an answer something like 639.35 meter cube. So the cost of water would be 639 times 40 rupees. The person charges 40 rupees for the water. Okay. So if I multiply this by 40 and add on to the previous 99 lakhs we had, so it gives me a total cost. Okay, let me just quickly wind up. Total cost for pit A should come out to be, okay, value times 40 plus the 99 lakhs. I think it should come out to be something like 99 lakhs 95,594. Okay. What about pit B? This was pit A. 2 minutes? We'll just take 2 more minutes please, just to wind up. Pit B, I would like to follow the same logic. I have void ratio equals to volume of voids over volume of solids. Okay. Volume of voids gives me equals to the void ratio at pit B is 1. So that equals to 1 times volume of solids. Okay. In other words, total volume equals to volume of solids plus volume of voids. Volume of voids is equal to volume of solids. In case that equals to 2 into, okay, what was the number? Okay, let me hunt for this number. The 988. Okay, so 2 into 5988, it gives a value of 11976 meter cube. That's the total volume. The cost of earth equals to rupees 900 times this number. Okay, so it gives a value of rupees 107 lakhs 78,400 rupees. Okay, the cost of water is free. This pit D supplier gives free water. However, despite giving free water, this person, this chap is more expensive than the pit A. Okay, so his freebie or his free water is no good. So I would say borrow pit A is economical. Okay, now if you have followed the logic, I would like you to go home and try question number 3. Okay. If you have any questions, we'll be glad to take a few questions, you know, 1 or 2 questions maybe. Any questions, please raise hand. I'm not sure how you're going to raise hand. Yeah, yeah. Okay, we have DCRU teacher. I'm sorry, we can't hear you. Your face is also at one corner of the screen. We can't hear you. I'm sorry, we can't hear you. I'm not sure whether yes. No. Could you please check the audio, or if or could you put your question on chat window, or check the audio again, please? Okay, we'll come back to you. Please do that check thing. We'll come back to you. Right now, we'll go to this AITM.
Sir, good morning, sir.
Yes. Good morning.
Sir, good morning, sir. I am Hamanantra from Aditya Engineering College. Sir.
Yes. Yep, I can hear you. I can hear you. Please continue.
Sir, good morning, sir. Yes.
Yeah, I can hear you. You're clear.
Sir, are we audible, sir? Hello? Hello?
Yes, yes, it is audible. Yeah, maybe. Hmm? How many do we have? Okay, so what do we do? Okay, we had two questions. I'm not sure if someone has, if you can just put your question on chat, because we are not able to, connect through. We'll be glad to answer. Okay. Okay. Hmm? I'm not sure if they are with us. Are they, are they on the same class? I think it's fine. No one is speaking. Okay, if there are no questions, we'll close this session. Okay, we have to close the session. I thank you all for being there. But in case you have a question, please do email to me. I'm back this week. I was away over the weekend. for last 3-4 days. I'm back. I will be glad to answer any question if you put them.